Fundamental of Electric Circuits and the Historical Development, organized by the Department of Physics, Nabadwip Vidyasagar College. This is the sixth webinar that we are organizing from the last 2 months. We are happy that we managed to organize a webinar on electric circuits, which is very common in our day-to-day life. Our speaker will definitely elaborate the topic with more details to keep it more exciting to you. Our college has made a lot of advances in the e-learning initiative. Along with the faculty, the support from our principal sir is a great factor too. After all, a speech is only as good as its captain. Now I want to request our principal sir, Dr. Shapon Kumar Roy, to deliver a welcome address. Principal sir, please.
Can you hear me, Nirmalendu?
Yes, you can start.
Thank you, Dr. Nirmalendu Ganguly. We know that the Department of Physics, in collaboration with the IQAC, is organizing this national webinar. We have with us Dr. Sanjib Ganguly, who is associated with the IIT Guwahati, Department of Electronics and Electrical Engineering. I express my thanks and gratitude to Dr. Sanjib Ganguly as he has accepted our invitation and agreed to speak on fundamental of electric circuits and the historical developments. We thank Sir from the Department of Physics in particular and the Nabadwip Vidyasagar College in general. Thank you, sir, for giving your consent to be a speaker on this topic, fundamental of electric circuits and historical developments. I actually express my thanks and gratitude to the convener of this webinar, national webinar, Dr. Prabhas Mondol, organizing secretary, Dr. Organizing Secretary Sri Professor Nidarshana Guho, and the members of the organizing committee, Dr. Nirmalendu Ganguly, Professor Rajkumar Mondol, Dr. Asim Kumar Bishwas, and Professor Sudipto Maduk. I express my thanks and gratitude to all of you for helping or arranging such type of webinar. And I express my thanks and gratitude to Dr. Bhaskar Chatterjee, who is the coordinator internal quality assurance at Nabadwip Vidyasagar College. Special thanks to our president, governing body, Sri Biman Krishna Saha. Actually, his endless advice in this regard is always our asset from the viewpoint of expressing his desire to make this webinar a successful one. The participants who have joined from different corners of the country, I also express my thanks to thanks all of the participants who have joined this webinar. I hope the valuable speech and encourageable speech to be delivered by Dr. Sanjib Ganguly will enrich and enlighten the participants. Thank you. Thank you all. Over to Dr. Nirmalendu Ganguly.
Yeah, thank you, sir. Now I request Dr. Prabhas Mondol, Head of the Department of Physics, Nabadwip Vidyasagar College, to say something about our webinar. He is also the convener of this webinar. So, Prabhas, please.
Thank you, Nirmalendu. Good morning. I welcome all the participants on this digital platform. First of all, I express my deep sense of gratitude and respect to our respected principal, Dr. Shapon Kumar Roy, and all the participants on this digital platform. Without their participation, this seminar would not be possible to organize. Thank you all. Thank you, sir. Thank you, Dr. Sanjib Ganguly. Thank you, sir. Over to Dr. Nirmalendu Ganguly.
Yeah, Uh, Thank you, Pravada. All the participants are requested to mute their microphones, keep their video off, and not to share their screens throughout the webinar. If you have any relevant questions, then please post them in the chat box. You will definitely get an answer to your question from the speaker after the lecture. It is my pleasure to introduce our speaker, Dr. Sanjib Ganguly. Sanjib Ganguly obtained Bachelor of Engineering degree in Electrical Engineering from Indian Institute of Engineering, Science and Technology, IIEST, Sibpur in 2003. He received Master of Electrical Engineering degree from Jadavpur University, Kolkata in 2006. He completed his PhD from the Department of Electrical Engineering, Indian Institute of Technology, Kharagpur in 2011. He worked in the Tata Power Company Limited as a senior officer, electrical maintenance of 2 into 500 megawatt thermal power units in Trombay Thermal Power Station, Mumbai from 2006 to 2007. He worked as assistant professor in NIT Rourkela from 2011 to 2015. He joined the Department of Electronics and Electrical Engineering, Indian Institute of Technology, Guwahati in 2015. He is presently working as associate professor there. His research interest includes distribution system planning and optimization, multi-objective optimization, hybrid energy systems, custom power devices, and evolutionary algorithms. He has published more than 33 research papers in highly reputed international journals. Now it is the time to request our honorable speaker, Dr. Sanjib Ganguly, to start today's lecture. Sir, please start.
Okay, so thank you, Dr. Nirmalandu Ganai, and thanks to Professor Rai and Professor Mondal. My voice is audible, no?
Yes.
Okay, so let's start this seminar. So I welcome to all the students who are participating to this seminar. My screen is visible, no?
No.
It's not visible?
You are visible, not your screen. Just again do the present now, this option. Yeah, now it is coming.
Is it coming?
Yes. Yes.
Okay. So it is visible and my voice is also audible, no?
Yes. Now you can proceed. Yeah.
Okay. So I welcome to all the student who is participating in this seminar. I really do not know what is the syllabus of BSc Physics and how much knowledge you have in electrical science. So let's start from the very beginning. Okay. I hope that my English is also understandable to you. I'll speak very slowly. Okay. So can you imagine a world that we have presently? We also had this similar kind of world 150 years ago. Okay, you know that industrialization was started in Western world almost a century back. Okay, there was everything since 1890 up to 1900. That means it is of 90th century. There was everything except there was no electrical power. Okay, so there was a huge space of development. In fact, steam engine started running during that span of time in Western world as well as in our country. Although that time we were under British rule, but we had this steam engine much before we had the electricity. Okay, so there was almost everything except electricity. Okay, so people started thinking that what was the major difficulty without electricity that time was when sun set and darkness covered, people didn't have anything to do. Okay, so whole night part was unproductive. Okay, so people started thinking how to lit up the world. Okay, how to lit up the world, how we'll get a world with lighting and all. Okay, so this thinking process later on was translated into a huge development. Okay, so in this seminar I will briefly tell you this development along with very fundamental terminologies in electric circuit, and then finally I will show you how to solve. Means before that I will show you what is electrical circuit, what are the different components electrical circuits have, and many things. Okay, so let us move. Okay, so first thing that in electrical science is important to understand the concept of charge. Charge is the most fundamental component of electricity, and charge, electrical charge, it lies within the atom itself. As a physics student, you know better than me, in fact. So charge is the most fundamental quantity. Okay, and and we have negative charge in electron and equal amount of positive charge in proton. Okay, and the magnitude of charge a electron has is in an order of 1.60602 into 10 to the power minus 19 coulomb. Coulomb is the unit of charge. I hope you know it. It is named after the very famous French physicist Professor Coulomb. Okay, but what is more interesting that since this one electron carries that much of charge, then 1 coulomb of charge is equivalent to 1 upon this, that is equal to 6.24 into 10 to the power 24 electrons, and that is a very big number, 10 to the power 24. So it's a very big number, and that is why we have various equipment which can hold charges. Okay, one of the equipment is called capacitor. Okay, and we use in our laboratory the capacitor, and in fact we use it in our day-to-day appliances that you use in your home for various purpose. Okay, but that capacitor generally can hold charge in an order of microfarad. Microfarad means 10 to the power minus 6 farad, which is a very small unit as compared to this number 10 to the power 24. So this 1 coulomb, this means, what I mean to say is that 1 coulomb of charge is a very huge thing. Okay, and presently that no electrical appliance can hold that amount of charge. Okay, so charge is the most fundamental component of electricity. Okay, now charge was existing, but we could not hold it. The first concept of charge was discovered by Professor William Gilbert. Okay, in the year of 1600, long time ago. Okay, so what he did, he invented a device which can detect the statistically charged bodies. Okay, which can detect the statistically charged bodies. So that was the first invention in terms of electrical science, and that's why he is often called as the first electrical engineer in the world. Okay, afterward Coulomb, he detected the Coulomb, he invented the Coulomb law and electrostatic force of attraction repulsion, and this unit of charge is named after him. Okay, but much before that, Gilbert in 1600, means Coulomb invented, that was around end of the 18th century or beginning of the 19th century, but much before then, that 2 centuries ago, Gilbert invented a device which can detect the statistically charged bodies. So it can detect the charge. Okay. Then next, the fundamental concept is concept of current. Okay. Now, when charge moves from one part to another part, it creates an electrical current. Electrical current is nothing but rate of change of charge, electrical charge. Okay, so the motion of charges create electrical current. So here you, in this figure, you can see there is a battery, okay, which is connected to a simple conductor, simple wire who is having some conductivity. Okay, so if we have so you can see the charges will flow and thereby current will flow. Okay, and the convention is that current flow as the movement of positive charges, that is opposite to the negative charges. So whichever direction electron flow, just opposite direction current will flow. That is what the convention introduced by Benjamin Franklin in 1706 to 1790. You can keep on remembering these years, which are very important. Okay, 1706 to 1790. In fact, electricity, later on I will show you, was invented in the form that we have right now in the year of 1890 or so. But much before that, it's this component, or it's what we call the path was detected by various physicists and professors. Okay, so here you can understand one thing: the flow of electrons create an current, and the direction at which this flow of electron is there, in the opposite direction current will flow. Okay, that is what the convention is. And the mathematically, this current relationship was proposed by Anne-Marie Ampere, again a French mathematician and physicist. You see, all these are discovered by physicists only, the people who are expert in physics, because electrical science is nothing but a branch of physics only. Okay, so Anne-Marie Ampere was defined this electric current and developed a way to measure it in the year of 1820, and that is why unit of current is named as ampere. Okay, and what is that ampere? As I said, it is mathematically represented by the rate of change of charge, dq dt. Okay, it is mathematically represented by the rate of change of charge, dq dt. Okay, so from this expression you can understand. And if you have this if you can find out the expression of current, alternatively if you integrate it over a certain interval, you will get that how much charge transfer happened. Okay, all right. Next is the point that I want to tell you, that there are two types of current. One is called direct current, another is called alternative current. Direct current means it is called as DC. Okay, direct current stands for DC. Okay, so this DC or direct current, it remains constant over the time. If you plot this current with respect to time, it will remain constant. Okay, so this x-axis is the time, y-axis is I, so it remains constant. Okay, whereas alternating current, it varies with time. Alternating current is AC current, so it varies with time. How it varies with time? Like this. So this is a typical type of variation, and you know this is a sine curve. So this AC current is basically showing you sinusoidal variation, but it doesn't mean that AC current has to be sinusoidal. It can be of any shape. It can be a triangular, it can be a trapezoidal, or it can be of like a square, or many variation. But we choose sinusoidal variation of this current in AC circuit or AC power system. Okay, why we choose sinusoidal variation? Because you know, I hope that you know sine curve. You know, the sine has a very good property. If you differentiate it, it will be a cosine. cosine is nothing but a sine. It is sine pi by 2 plus theta is cosine only. Okay, so even if you integrate it, you will get a cosine. Cosine shape is also nothing but a shape of sine, so it doesn't change its shape even if you integrate or differentiate. Okay, it remains of same shape. So that is what one of the advantages of AC. Okay, and AC with sinusoidal waveform. Okay, so this time dependent characteristics we call current waveform. Okay, all right. And as I hope you understood the difference between DC and AC. DC always remains constant, same magnitude, and AC, it magnitude varies with time. Okay. Now there is another fundamental concept which is voltage. Now I hope that you I hope that you know what is electric potential. Suppose I have a point over here. What if it has some potential? Then how to define this potential? It is nothing but the amount of work you need to do if you want to bring a unit charge from infinite distance to that point. Okay, so similarly at this point B, its potential is defined in similar way. Okay, and if you take the difference between this potential of this point A and point B, whatever you will be getting, that is called voltage or potential difference. So voltage or potential difference is the energy required to move a unit charge through this element. Okay, all right. So for DC circuit, you have a voltage which will be having voltage waveform which will be having similar to this DC current. Similarly, for AC circuit, you will be having a voltage waveform similar to the AC current. Okay, so voltage waveform and current waveform would be similar, and based upon this, we have different types of electrical appliances historically invented. So some appliances are of DC appliances, some appliances are of AC. Okay, but presently most of almost everything is of AC. Why it is so, I will explain. Okay, now before that you need to know who has invented this voltage and why this unit is named as volt. Okay, because it is named by an Italian physicist, okay, who invented electrical battery, and that is on the in honor of Professor Volta. The unit of voltage is named. Okay, and he is that person. And now I think everybody knows, even whoever is illiterate, everybody knows that his name voltage. If you go to market to purchase any sort of electrical appliance like a electrical bulb or tube or whatever electrical fan, you will see on the top of that it is mentioned that how much voltage is the capacity or rating of that particular device has. Okay, then another fundamental component, that is power or energy. What do you mean by power or energy? Both are means energy is nothing but power multiplied by time. Okay, or power is nothing but rate of change of energy. Okay, now how do you get this power? There are various ways, but here I will show you how to get instantaneous power. Instantaneous power means, as you can see, voltage and current for AC, they are changing, their magnitude is changing with time. So for at any instant, if you want to if you multiply simply this voltage and current, whatever power you will be having, that will be the instantaneous power. And since this it is a quantity which is a function of two time varying quantities, so it also vary with time. Okay, so here you can see that this suppose the voltage across this particular element. Okay, and this is the current which is flowing through this element. So if you multiply these two, then you'll get the instantaneous value of power. And since voltage and current, they are time varying, if it is AC, then this power will also vary with time. Okay, and for DC, both this power will remain same, since voltage and current will remain same. Okay, now depending upon the direction of current and this voltage can be positive or negative, current can be positive or negative. For example, if this direction you consider that current is positive, then if current flows opposite direction, then current would be negative. Similarly, voltage will be high if this potential is higher than this, we will be having positive voltage, but if this potential is higher than this, we will be having negative voltage. Now if you multiply V into I, then if you come up with a positive value, that implies that you are consuming power, and if you get a negative power, that implies that you are generating power. Okay, power can be either generated or consumed. Okay, so power generation normally takes place in the generator, okay, electrical generator, and consumption takes place all other electrical appliances, or in there we call them load, electrical load, like your bulb, your fan, or many other equipment, your mobile phone charger and all. Okay, and the unit of this power is named as watt, and since, as I told you, the energy is nothing but power multiplied by time, so unit of energy is watt hour. Okay, now I will explain the development, how this world is lit up with electrical power. At the end of 90th century, at the year of 1880 to 1890, there was a huge development. If you look at my previous few slides, you will see that all these concept, voltage, current, charge, watt, etc., were established much before we had this electrical power system. Okay, the electrical power system means the system from which you are getting power. Okay, in your home also you have a some wiring, electrical wiring, that is a small set of power system. In fact, you can look at outside, there is a transformer from which the wires are coming, and then you are getting in your home electrical energy which is drawn by a cable which is connected from the local distribution circuit to your home. So these all are the part of electrical power system. Now how it developed, when it developed, that is what the important question. Okay, now it started developing at the year of 1880 to 1890. Okay, so when it was developed, there are two persons that probably you know. One is called Thomas Edison, who is the inventor of electrical bulb. He had a company who first started generation of electrical energy, and then to supply some few customers, 59 customers. Okay, but his system was DC system, direct current system. Okay, and there was another person who was genius, Nikolai Tesla. I'll show you his photograph. He initially started working with Thomas Edison. Okay, and there was a generator commissioned by Thomas Edison, from which electrical supply was given to some few customers. But DC system, he was facing different problems. Okay, and Tesla was trying to sort out these problems, and finally he come up with some solution as well. But finally Tesla realized that the system will not work, and due to some other reasons, so he left the job of Thomas Edison and he joined with Westinghouse. He's a genius. He had developed a alternative current system, that AC system, and he also developed a motor which run by AC. And that motor, motor means it's a electrical appliance which convert electrical energy to mechanical energy. You use motor to pump water from your ground stair to your top of your home, that is where your water tank is located, or you use electrical motoring for various purpose. Okay, now the type of the electrical motor that we are using till today, was actually invented by Tesla, and it was called as induction motor. It works with electricity, electromagnetic induction principle, okay, which was discovered by Michael Faraday. Okay, now there was an exhibition at 1884, which was initially rolled out the whole thing. Okay, so that exhibition was arranged by American Institute of Electrical Engineers, okay, which was nowadays famous Institute of Electrical and Electronics Engineers, IEEE, and that was the first kind of technical conference where they made various various scientists etc. joined, and they had shown their innovations. Okay, all right, and Edison joined this exhibition. Nikolai Tesla also joined, and there are many others from Europe, because that whole thing was either developed either in Europe or in USA. Okay, so you have seen that Volta, this Ampere, all are European people only, people from France, Germany, Italy, and all, and English also, and some are people of USA. Okay, now they came together and exhibited their inventions. Okay, this was the first step toward developing the electrical power system from which you are getting power nowadays. Okay, and there was a various development took place. Spark produced DC motor similar to in AC motor developed by Nikolai Tesla. DC motor was also developed, but in the meantime there was a development of transformer. Transformer is a name that everybody knows. You need not to be a physicist or electrical engineer to know this name. Now, what is the purpose of transformer? Transformer generally changes the voltage level from one voltage to another voltage. The transformer that you have in your locality near to your house, it changes the voltage level from 11 kilovolt to 440 volt. Okay, so this transformer is a huge development for advocating this AC power system. Okay, and this change of this transformation of voltage level was very, very important. Okay, so this, after this discovery of transformer, this AC system, there was a battle, between AC system and DC system. Thomas Edison and his team was advocating for DC system, and Nikolai Tesla and Westinghouse, they are advocating for AC system. And then finally AC system won over DC, and thereafter all this electrical power system that you are nowadays seeing everywhere in the world are of AC system. And that system was developed, or mastermind behind this system was this genius Nikolai Tesla. Okay, so he was a Austrian. He was born in Austrian Empire. Nowadays it is Croatia in Europe. Okay, and later on moved to USA. So he initially pointed out the problem with DC system and developed this AC power system. Okay, for him, if you want to know, there is a website, web link that you can click, that is called Tesla Society in USA, and you will get to know various things on him. Okay, and one thing that I should point out, that Nikolai Tesla was very, very much impressed on this Swami Vivekananda. Okay, in fact Swamiji visited that time to USA, and you can see that they had a very good contacts between this Tesla and Swamiji. If you go to this link, you will get to know. In fact, Swamiji philosophically was saying various things to Nikolai Tesla, and Nikolai Tesla was trying to mathematically prove this thing. Okay, so very good document you can get from him if you go to this site. And in fact, if you go through this book of Nikolai Tesla, you will find that various terminologies he took from Vedanta, like prana and various force, etc., was named by various Sanskrit words like prana and all. So he was very, very impressed by Swamiji. Okay. Now, after this development, from 1896 onward, this AC system started working all over the world. Initially, there was a generator located at Niagara Falls, which was 20 miles away from the locality, and power was generated and brought out from this Niagara Falls, which is far away. 20 mile was in that time far away in terms of electrical length to bring power. Okay, and then several private companies started developing this electrical power system, and in fact in our country also under British rule, the first electrical power station was developed in Darjeeling, that was hydro power station. And then slowly the things changed. Means you get electrical energy and you used it for various purpose. Okay, this was my discussion on the history. Okay, now let us see how this what is electrical circuit is all about, and what are the different components, and some basics law to describe the electrical circuit or to analyze the electrical circuit. Okay, so basically electrical circuit is a closed path through which DC or AC current or power flows. Okay, it consists of various elements. Some of the elements we called as sources who can generate power, and some of the elements we call passive elements which either consume or store or convert power. They are like resistance, inductance, capacitance. And there are some devices which are partial conductor like semiconductor. Okay. Okay, so as I said, there are two types of sources. One is called independent source, another is called dependent source. Independent sources are those sources who can generate power irrespective of dependence on any other element. So for example, this is an type of independent voltage source who can provide voltage across these two terminals irrespective of any element. Okay, this is a current source, independent current source, who can give you constant current or variable current at this particular terminal irrespective of any element in the circuit. Okay, but there are some dependent sources as well which are named as voltage control voltage source. Those sources in those sources, for example, this is an example of voltage control voltage source. So here the voltage magnitude depends upon some other voltage source in the circuit. Okay, similarly this a current control voltage source. So this is an example of current control current source and so on. Okay, I am not going detail on it. Okay, now there are some element as well. One is called passive element. These all elements are classified into two types. One is called passive element, like resistance. I hope that you know what is resistance at this moment. Or inductance, capacitance. Inductance is a device which can store electrical energy in the form of magnetic field, and capacitance, it stores electrical energy in the form of electric field. So these two are basically energy storing devices, but they are widely used in electrical circuits. And resistance, I hope you know what it is. There are some elements which are active elements like diode, transistor, other semiconductors. So these elements can partially generate. They are associated with partial generation and consumption as well. Now you see, this is a typical electrical circuit shown over here. Okay, this is a typical electrical circuit. It consists of some generating sources, like this is a voltage, independent voltage source having a voltage 10 volt. This is an independent current source having a current of 2 ampere. This is a DC circuit, meaning that this voltage and current are constant over time, because AC analysis is somewhat complex, so I am not going into detail on that. Okay, so they are DC. This is a DC circuit, and this is for the sake of your understanding only. Okay, now these three are the different resistances: 5 ohm, 2 ohm, and 3 ohm. Okay, now before we go to the analysis of electrical circuit, you should know some of the non-convention, some of the convention we use, like nodes. What do you mean by nodes? Electrical nodes. The node is that basically the junction between any two branches. So these all elements are individual branches of the circuit. Like this is one branch between this node and that node. This is another branch between this node to that node. This is another branch, and so on. So we have 1, 2, 3, 4, 5 branches, and here all are interconnected. So practically they are same point. Okay, and they are having same potential as well, because they are connected together like this. Okay, so we have 1, 2, 3, 4, 5 branches, like CA, AC, AB, BC, and so on. Okay, similarly we have few nodes like A. This node, these three are same node because they are having same potential. They are just connected, okay, with a wire. So this is a single node. Similarly, this is a single node C. This is one node. Okay, and we have some loop. Loop means a closed path, like a path starting from this node to C to A, B, and then C. So this forms a loop. Okay, like A, B, C, A, B, C, A. So this also forms a loop. Okay, now if you have that similar kind of electrical circuit, you can analyze it. Analysis means if you have this circuit with this given information, you can find out the voltage and current across any of the node and branches. For example, here the voltage is somewhat given at 10 volt, but at this point, at this node B, the voltage is not given. Now how to find it out? This you can find out with the analysis of the circuit. Similarly, what is the current that will flow through this 5 ohm of resistance? What is the current that is flowing through 2 ohm of resistance and this 3 ohm of resistance? All these things you can determine with the analysis of electrical circuit. Okay, now how do we analyze the electrical circuit? Again, we have to follow the rule or laws proposed by or invented by proper German physicist Gustav Robert Kirchhoff or Kirchhoff. Somebody tell Kirchhoff, somebody tells Kirchhoff. Okay, so based upon that, there are two rules. One is called Kirchhoff current law, another is called Kirchhoff's voltage law. So these two are widely used anywhere in electrical circuit. Wherever you have electrical circuit, the first tool that to analyze the electrical circuit to determine the voltage or current is to apply either of these two rules. Okay, one is called KCL, Kirchhoff's current law. Another is called KVL, that is Kirchhoff's voltage law. Okay, now what is these two rules all about? According to this KCL or Kirchhoff's current law, the algebraic sum of the currents entering a node is 0. Okay, all right. What is that? What does it mean? Suppose I have this node A. Okay, so there are two branches which are coming out to this node A. Now if we apply this Kirchhoff's current law, then current which is coming at this node A from this side and current which is coming out coming from the at node A from that side, if you sum up then their magnitude should be equal to 0. If you add it, or their magnitude will be 0. Or alternatively, you can think the all incoming current will be equal to all outgoing current. Okay, so this is nothing but Kirchhoff's current law. And Kirchhoff's voltage law is, if you sum up, if you take algebraic sum of all voltages around a closed path or loop, it will be 0. That means at this circuit, if you add the voltages from here, this branch, that branch, and that branch, and if you add together all these voltages, then their magnitude should be 0. Okay, so these two are used for circuital analysis, and the application of KCL, that is Kirchhoff's current law, is called node analysis, because this is somewhat related to node. And application of KVL is called as mesh analysis, because it is somewhat related to loop or mesh. Okay, now I will show you how to solve a circuit using node analysis by using KCL. Okay, suppose this is the circuit as I have shown you, and I have to apply KCL for the circuit in order to get the voltage at this point, node B, because voltage at node B is known to it is unknown to us. Okay, voltage at node A is known to us because it is equal to 10 volts. So this 10 volt source means with respect to that node, this potential is 10. Okay, but I do not know what is the voltage at this node B. So that I can determine with the help of node analysis, or with the help of Kirchhoff's current law. Okay, first thing that you have to do, that you have to consider a reference node. Here, you know, in the downside we have this node C, so we consider is a reference node, and we consider its potential is 0, that is VC is 0, voltage of this C is 0. Now with respect to this potential A is 10 volt, as this is showing that this potential of this point with respect to that point is 10 volt. Okay, so VA is equal to 10. Now how do we get VB? We can, in order to get VB, simply I have to apply Kirchhoff's current law at this node B. How do we apply Kirchhoff's current law? Simply I will find out what should be the expression of that current flow through this 5 ampere of resistance, and then that will be equal to what is the current which is flowing from flowing through these 3 branches, and that will give you the solution. Okay, now the current which is flowing from point A to B through this 5 ohm of resistance is nothing but the potential difference, because you know, according to the Ohm law, your current is equal, voltage and current, they are proportional, and V is equal to IR for DC circuit. So the current which is flowing from A to B can be written as the potential difference between VA and VB divided by 5 ampere. Okay, so that is equal to VAB by R. Okay, so that will give you the current which is flowing from A to B. So since I know this VA is 10 volt, so you can write at 10 minus VB is equal to 5. Okay, so if you similarly, if you determine what is the current which is flowing from node B to C, there are 3 components of current that will flow. One is through 2 ohm of resistance, another is through 3 ohm of resistance, another is that current source itself. Okay, now what is the total current? So for doing that in similar way, you can calculate that what should be the current which is flowing from B to C through this 2 ampere of resistance, that is VB minus VC is divided by 2 ampere divided by 2, that much ampere. Similarly, current which is flowing from through this 3 ohm of resistance is VB minus VC divided by 3. And since this we are determining the current in this direction, so this 2 amperes should be negatively added, because in this direction if it is positive, opposite direction it will be negative, so this is minus 2. Now if we equate this and this, since we know VC is equal to 0, then we will be having only one unknown left, that is VB. Okay, and then VB you can calculate, and that is coming out to be 3.87 volt. Okay, you yourself can try also. Once you get VB, You can find out what is the current flowing through this 5 ampere and all. Everything is possible. In fact, what is the power consumption at this 5 ohm? What will be the power consumption as 2 ohm and everything. Okay. Now, I will show you how to do mesh analysis. Okay. For mesh analysis, as I said, we need to apply Kirchhoff's voltage law, that is KVL. And to do that, you have to first find out the loops. So here in this circuit, you will see there are two loops. One is this loop, another is that loop. And what I need to do, first I need to assume that at this loop I1 current is flowing, at this loop I2 current is flowing. Okay. And we have two types of sources here. One is 15 volt source, another is 10 volt source. Okay, there is no other sources, all other resistance only, 5 ohm, 6 ohm, 10 ohm and 4 ohm. Okay, I hope that this symbol is ohm, that you can understand. Okay, now we use this KVL first in this loop and then in that loop. Okay, how to use KVL? So what, as I said, the summation of voltage across all these elements in a loop should be 0. Okay, so first you take what is the voltage across this. If we take this current is flowing clockwise, then this voltage is 15 volt. Okay, then what is the voltage across this? This will be 5 multiplied by this I1. Okay, and this is why it is minus, because voltage, if it drops, if you take in the direction of current, it drops means it is negative, and voltage in the opposite direction of current is rising, so in that direction it will be plus. So in that way, so voltage across this will be minus 5 into I1, and voltage across this 10 will be in the minus, that is 10 multiplied by I1 minus I2, because through this 10 ohm resistance, I1 is flowing through this direction, but I2 also is flowing through this direction. So resultant current is I1 minus I2. Okay, minus 10 again, if you go from positive to negative, voltage will drop. So minus 10 is written, and then their summation is 0. In similar way, if you apply KVL at this loop 2, you will be getting this equation. Now you have two equations and you have two unknowns. One is I1, another is I2. Okay, if you solve it, you will be getting their values, which are coming out to be same, that is 1 ampere. You can solve it by yourself. Okay, so finally I come to the end of this lecture, and for this type of analysis or circuits or any other information, the basic book is Charles K. Alexander and Matthew Sadiku, Fundamental of Electric Circuit. It's McGraw-Hill publication, but its edition in India is also available, that is Tata McGraw-Hill. Okay, and finally, thank you for your attention.
Yeah. Thank you. Thank you, sir, for your beautiful lecture. Now we can take question from the audience if they have some. Let me check chat box. Yeah, one question is from Otonu Nondi. He is saying that what is the physical source of resistance in the circuit? Physical explanation, not the mathematical relation. Means he want to ask what is the physical explanation of the resistance in the circuit?
See, resistance means any circuit or any element which is having some resistivity. Okay, so if there is no element which is having perfect conductivity, there is nothing, no element except some sort of superconductor. Even that superconductor is having some sort of resistivity as well, but ideally there is no conductor which is having full, means 100% conductivity. Okay, so if there is no if it is so, then that means there exists some sort of resistivity, and that resistivity is, is a source of resistance. And if you ask me, I could not understand the question properly. If you ask me what is the type of register, then I will show you. I can tell you, you know, that in laboratory we use some rheostat. Okay, rheostat is nothing but in a foil we have a very long conductor wound over there, and that conductor is not perfectly conductor. It is having some sort of resistivity. It cannot produce 100% conductivity, and that resistance is the total resistance of the particular element. That is the total resistance of the rheostat. Okay, so resistance is in physics of the behind this resistance is whoever is not fully conducting having some sort of resistivity.
Okay. Next question is from Nadir Mondol. He's asking what discussion about supernode and super mesh analysis.
Okay, so supernode I didn't kept in this lecture. Assume I didn't have any idea that you knew that. Supernode, you can, for suppose this circuit, instead of having a very small one, if it is a very big circuit, then we can make some of the nodes together to form a supernode. Okay, so the example I do not have at this moment, but it is just for the sake of your analysis. We make it simpler circuit from a very big circuit.
Okay, so there is no more questions. So we want to inform all the participants that a link of the feedback form will be sent to your registered email address today. After the submission of your valuable feedback, you will receive your certificate of participant through your registered email. Thanks to all of you for your active participation in the webinar. Hope that all of you enjoyed the webinar and enriched yourself. I want to thank Dr. Sanjib Ganguly for his splendid lecture, and we are grateful that he has accepted our request and agreed to deliver a web lecture. I also want to thank our principal sir and coordinator IQA for their active support. Last but not least, I want to thank all of my colleagues for their continuous help and cooperation. Thank you and goodbye. See you soon. Thank you, sir, for your lecture. Thanks. So,
Okay, thank you.